The modern automotive chassis is a rolling data center. Mechanical control systems have been almost entirely replaced by centralized computing and AI-driven control networks. In the past, engineering vehicle safety meant calculating the deterministic physical wear and tear of hardware parts. But software-defined vehicles introduce a non-deterministic complexity. You cannot calculate the physical fatigue of a machine learning algorithm. Regulators mandated 4 frameworks: ISO26262 for hardware faults, SOTIF for edge cases, ISO21434 for cybersecurity, and ISO 8800 for AI safety. In practice, these operate in total isolation. Security, functional safety, and AI teams are completely cut off from one another. Treating an interconnected network as 4 separate compliance checklists creates the architecture's most severe vulnerability. When engineers apply a safety mitigation in one specific domain, they frequently engineer a fatal architectural flaw into another. In systems engineering, this is a structural trade-off. Because computing resources and response times are finite, over-optimizing for a single regulatory metric mathematically degrades another critical function. Without a unified view of the architecture, the vehicle is programmed with deeply conflicting commands. These contradictions lie dormant in the code, waiting for a specific sequence of real-world events to trigger them. Passing independent safety and security audits provides a dangerous illusion of protection. It merely masks a systems-level collapse waiting to execute. Consider a steer-by-wire system operating at highway speeds. A minor processing error causes a momentary delay in a sensor data packet. Functional safety protocols instantly classify this as a random hardware fault. To maintain driving capabilities, a principle called fail operational, the system commands a rapid warm reboot and immediately shifts control to a backup processor. Simultaneously, the cybersecurity protocol scans that exact same delayed packet. It flags the anomaly as a message spoofing attack and demands an instant network lockdown to contain the perceived hacker. Here is the architectural collision. The strict security lockdown actively blocks the safety relay from accessing the backup controller. By severing the connection, the system causes a total loss of steering. Even standard operations create mathematical conflicts. Heavy cybersecurity encryption requires processing time. This computational latency eats directly into the millisecond fault tolerant time interval that functional safety demands for emergency reactions. By strictly following regulatory protocols to protect the car from hackers, the system executes the exact fatal crash the safety team engineered to prevent. This tension also exists between environmental limits and vehicle availability, particularly in AI-driven autonomous emergency braking systems. If a vehicle encounters dark shadows or distorted cargo, the AI vision model struggles to classify the shape, causing its predictive confidence level to drop. This graph illustrates the SOTF mandate. It requires a deterministic safety cage, a rigid set of rules that trigger highly conservative reactions the moment the AI's confidence dips below a strict threshold. Because the safety threshold is tuned to be hyper-cautious, it generates an explosion of false positives. The vehicle aggressively slams on the brakes for ordinary shadows. Over-indexing on single-vehicle safety thresholds destroys system availability. By commanding unpredictable stops on clear roads, it actively introduces secondary hazards, like multi-car rear-end collisions, into the traffic ecosystem. To resolve these deadly contradictions, engineers must abandon isolated risk spreadsheets and synthesize a multidimensional causal network. This is the FTMEA Matrix, the Integrated Failure and Threat Mode and Effect Analysis. It serves as the core engine for cross-domain engineering. We start by populating the root sources. We input 4 completely different triggers: a hardware bit flip, extreme sun glare, an OTA malware injection, and untrained AI data. Despite originating from 4 separate compliance domains, all of these triggers funnel into the exact same localized system behavior, the complete loss of the camera node. And that localized failure translates into the exact same catastrophic outcome at the vehicle level, a pedestrian collision hazard. This unified math allows teams to calculate a cross-domain correlation factor. When a security engineer applies a heavy encryption patch, they can mathematically calculate exactly how much that patch increases the functional safety risk of a late-breaking response. By mapping every domain's risk onto a single, common severity scale, engineers finally visualize and neutralize the true blast radius of their design choices. Tracking these complex cross-domain correlations is physically impossible using traditional static document structures. The solution is Model-Based Systems Engineering, or MBSE. It establishes a single source of truth, connecting vehicle behaviors, hardware, and software into one digital schema. Tweak a security node and a pulse travels through the model, automatically recalculating safety latency across the entire network. MBSE enforces bidirectional traceability. It exposes fatal engineering contradictions in a digital simulation long before the vehicle is physically manufactured. Even with perfect digital modeling, non-deterministic AI will inevitably encounter Area 3 edge cases, unknown and highly complex environmental hazards once deployed on real roads. This is where the deterministic safety cage operates dynamically. It constantly monitors the AI's confidence levels and, upon detecting a hallucination, gracefully degrades system performance to maintain physical control. The safety cage also initiates the AI Data Flywheel. It captures the anomaly data, encrypts it, and securely transmits the scenario to the cloud. There, the AI model learns from the anomaly, reclassifies it as a safe scenario, and pushes a fleet-wide over-the-air update. In the SDV era, safety is not a static certification achieved at launch. It is a continuous, living loop of encountering, learning, and neutralizing threats. Verifying hardware safety, cybersecurity, and environmental limits in isolated laboratory testing is no longer sufficient. Engineers must implement co-validation, the rigorous process of simultaneously deploying multiple vectors of stress against the unified vehicle architecture. First, you inject a blinding weather event into the simulation to cripple the AI's environmental limits. Second, you simultaneously trigger a CPU memory overload to mimic a random hardware fault. Third, you launch a malicious denial-of-service attack against the vehicle's network during that exact moment of maximum vulnerability. The architecture's true fail operational capability is only proven when the safety cage can successfully manage all three critical failures at the exact same time without losing steering or braking control. As vehicles evolve into highly centralized AI-driven networks, isolated compliance is a dangerous illusion. Fully integrated co-engineering is the only way to survive the complexities of the modern road.